All right, so back here. So now we're asked to find the velocity of the object between 8 and 12 seconds. If you have a position time graph, who can unmute and tell me how you find velocity? From a position time graph, how do you find velocity?
You take the position over time.
Yep, so what are you doing with the graph when you do that?
You find like where it is over what time. Like if it's like from 8 seconds to 12, you do 12 minus 8 to get 4 seconds. And then the displacement of it, like how much it is, like the final minus initial divided by the time.
So use a math word for me. If you were in math class and you were asked to do the same thing, the teacher would tell you to find what about the graph?
The rate of change.
Right, which means you're finding what? One word. Give me one word.
The slope.
The slope. So from a position time graph, to find velocity, you want to find the slope. So we're looking for the slope of that line between 8 and 12 seconds. So we're looking for, whoops. We're looking for this little piece right in here. So let's find the slope. So to do that, let's get our points first of all. So at 8 seconds, at x equals 8, our y value is right here. So it's about positive 15. And at x equals 12, our y value is 0. So remember, to find the slope, it's change in y over change in x. So we're going to subtract our y's, 15 minus 0, over, if I start with this 15, I've got to start with the x that goes with this when I'm subtracting the x's. So that's going to be 8 minus 12. Change in y over change in x. So I end up with 15 over minus 4. And if I go ahead and divide that out, that ends up giving me negative 3.75. And the units are going to be these units divided by these units, which in a position time graph are usually going to be meters and seconds. So meters per second. So this thing's got a negative slope. So again, somebody unmute and tell me what the negative 3.75 means here. What's the importance of the negative slope?
The direction.
So which way are we going? Assuming we're going horizontally.
The left.
Going to the left. So this object is moving to the left at a rate of 3.75 meters per second. Anytime you have a line that is sloping down and to the right, that's a negative slope. If you've got a line that's up and to the right, positive slope. This would be a positive velocity. This would be a negative velocity, assuming we're looking at position time graphs. All right, so let's go ahead and do the same thing with question 4. So again, let me clear off my graph. So what is the velocity of the object between 16 and 24 seconds? So we're looking at this part of the graph. Now, some people are going to look at that, and they're going to look at these numbers over here on the y-axis, and what wrong conclusion are they going to make? What do you think a common mistake people make when asked about this velocity when they look over here on the y-axis? What do a lot of them think? A lot of people think this thing's moving backwards. It has a negative velocity. It's going to the left during this time frame. That's not true. Let's calculate that velocity. And remember, if we want to get the velocity from a position time graph, we find the slope. So at x equals 16, our y value is about negative 15. And at x equals 24, our y value is 0. So find that slope. It would be change in y, negative 15 minus 0, over change in x, 16 minus 24. So that's going to end up being negative 15 over negative 8. Notice we've got a negative divided by a negative. That comes out to be positive. And 15 divided by 8 comes out to be 1.875. So our speed on number 4 is a positive value, 1.875 meters per second. And again, that means we're moving which way? Somebody unmute and tell me. Which way are we going if our velocity is positive?
Positive. Oh, right.
To the right. Or if we're going vertically, it would be up. All right, so that's position time graphs. Any questions on those?
I have a question.
Yeah.
Have you already posted the link for the Pear Deck?
I did. So you go to joinpd.com and you type in the code. Let's see. Let me go back to the Pear Deck. Give me just a second here. Yeah, so for those of you who joined late, joinpd.com, type in the code PWYVFX. And I'm going to ask you guys now to join me back at the Pear Deck again. Go back to your Pear Deck window. And we're going to go to the next slide. So notice here we're looking at a position time graph that has a curve. It's not a straight line. Can someone unmute and tell me what a curved position time graph tells you? Can anybody tell me what a curved position time graph means?
Acceleration.
Acceleration. Because what's changing? What's changing about this graph? What makes it curve? A curve means what quantity about the graph is changing?
The slope is changing.
It's slope. And we know that slope represents velocity. So if we have a changing slope, we have a changing velocity. And a change in velocity is what?
Change is the acceleration.
Acceleration. Now in this case, well, let's go to another graph here. So notice that we can have curves in two different directions. We can have curves that curve up. And we call those upward curves concave up. When you have curves that curve up, like you see the top line here on the Pear Deck slide, those mean that the acceleration is positive. On the other hand, you can also have curves that curve down, concave down curves. And you see those on the bottom line. So any of those, the bottom line, concave down curves mean that the acceleration is negative.
I have a question.
Yes.
Is this supposed to connect some way with calculus?
Yes. So it's really like taking a derivative. It's very similar to what we're doing right now. Taking a derivative is very similar to finding the slope.
Okay.
Are you in calculus now?
Yes.
Yeah. And you'll probably get to some problems in calculus
Yeah.
where you take derivatives to do what we're doing with algebra right now.
Yeah, that's what we're doing right now.
Perfect. All right, main thing to get from this slide, if you have a curve that's a position time graph, you have a curve that's concave up, the acceleration's positive. If on the other hand, you have a curve that's concave down, the acceleration's negative. That's the key thing. All right, we're not going to worry about that right now. So now we've got the next slide that has some interactivity to it. And I want you guys to answer for me, just on your slide. I want you to answer question 1. So just write in your answer to question 1. So it wants to know, is the object moving forward or backward? So just tell me forward or backward. And then in 2 or 3 words, tell me why you think that's true. So forward or backward, and justify. Tell me why. Talk about the graph. So again, go ahead and answer question 1 only right now. And your answer should be forward or backward, and then in a couple of words referring to the graph, tell me why you think that. Justify your answer. And remember on Pear Deck, I'm about to show some responses. nobody knows whose responses these are. I don't even know who wrote them. So it's anonymous. So nobody's going to be embarrassed if they get the wrong answer. Nobody knows who answered this, but I'm going to pull up a couple of your responses. Whoops. All right, so I'm just going to scroll through. If you guys see some forwards, backward, backward. There's a forward, a backward. So it looks like I'm getting about 50-50 here. So now let me end this. And I'm going to go back to my PowerPoint presentation. So if you guys will go back to just your Zoom window. This way I can write on the screen. So it wants to know, is the object moving forward or backward? Now, about half of you looked at this and you looked at this negative slope. And you said it's moving backward because the slope's negative. But notice what kind of graph this is. This is velocity versus time. This is not position versus time. This question is asking us if it's moving forward or backward. Really, we just need to look at the velocity. And in between 0 and 1 second, that velocity is always positive. It never becomes negative between 0 and 1 second. If it has a positive velocity, that means it's moving forward to the right. So the correct answer here was forward because the velocity is always positive. Now, another thing that you've got to think about on a velocity time graph, what does the slope represent on a velocity time graph? Someone unmute and tell me that. What does the slope represent in a velocity time graph?
Acceleration.
Acceleration. So the slope of this line is negative, which means even though we have a positive velocity, between 0 and 1 second, we also have a negative acceleration, which means what's this object doing between 0 and 1 second?
Decreasing.
It's slowing down, right? Because the sign of its velocity and the sign of its acceleration are opposite. Whenever that's true, the thing is slowing down. We want to know what's the acceleration between t equals 0 and t equals 1. So let's go ahead and find that acceleration. Remember, in a velocity time graph, slope gives you acceleration. So let's find the slope. So at time 0, x 0, the y is 4. At x equals 1, the y is 0. So find the slope, change in y, 4 minus 0, over change in x, 0 minus 1, and we end up with an acceleration of -4. And what are your typical units for acceleration going to be, guys?
Meters per second squared.
Yeah, so you could write it meters per second, these units, divided by these units, meters per second per second. That's one way to write it. And what that means is that every 1 second, the speed is changing by this much. Oftentimes, instead of writing it this way, most books are going to write it like this, -4 meters per second square. But this might be a way to help you think more about what it means. Every 1 second, this is how much the speed is changing. 4 meters per second toward the left, -4 meters per second. All right, so now let's go ahead and look at number 3. What distance does the object travel between t equals 0 and t equals 2? So you guys tell me how you find distance from a velocity time graph. Can anybody tell me how to find the distance from a velocity time graph?
Area under the curve.
Yeah, you find the area under the curve. Now, if you were in calculus, that would be taking the antiderivative or the integral. But this course is algebra based, so we're simply going to find the area under the curve. So we're going to go to between t equals 0 and t equals 2. So that would be in here. So I'm going to make a little rectangle right there and a little rectangle. Sorry, I said rectangle, I meant triangle. And I want to find the area of those two little triangles. So this first triangle has a base of length 1 and a height of 4. If you guys remember any geometry, you know that 1/2 base times height is how you find the area of a triangle. So for this triangle right here, that would be 1/2, 1 times 4. So that would give me an area of 2. Now, essentially what we're doing when we're finding the area under the curve is we're multiplying this quantity times this quantity. So what do we get when we multiply meters per second times seconds? What are meters per second times seconds?
Meters.
Meters. So we end up with 2 meters for the distance here. All right, now let's do the same thing on the triangle at the bottom. And again, it has a width of, or a base rather, of 1 and a height of 4. Notice we're talking about distance here, and I'll get the question in a minute, not displacement. So remember, if we're talking about distance, these signs don't matter. The direction doesn't matter because distance is a scalar. Someone was trying to ask a question. Go ahead. All right, we'll come back to you. Let me know if you come back to it. But the bottom triangle, area equals 1/2. The base has a width of 1. The height is 4, because remember, the signs don't matter because we're dealing with scalars. So again, that area is 2, which means the total distance this thing moved was 2 up top, 2 down on the bottom, a total distance of 4 meters. Now, notice the next part of this question, number 4. What is the displacement of the object? What again is the main difference between displacement and distance?
You take the final minus initial for displacement, but on distance you take the whole thing. Like even if it stops, you add that to it.
Yeah. So, but in reality, the main difference is in displacement. It's a vector. Direction matters. Distance is a scalar. Direction doesn't matter. So when we were calculating the areas under these curves, this area was positive 2. But if we're trying to calculate distance, what should this area of the bottom triangle have been?
Negative.
Negative 2. When we add those together, we end up with what displacement?
0.
0. So the displacement is 0. And the second part of this question asks, what does this mean about the object's motion? Well, in part A, in what direction was the object moving?
Forward.
Forward. And then in the second part, this part, it was moving backward, which means where did it end up?
Right where it started.
Yeah, it ended up exactly back where it started. And that's what a displacement of 0 means. It doesn't mean you didn't move. It just means you moved one way and you came back and you ended back up where you started. That's what happened in this problem. The thing moved forward and then it moved backwards. And at the end of the problem, it was exactly where it started. That's why it had a displacement of 0. Make sense? All right, I'm going to go back to the Pear Deck screen. So you guys switch with me and go back to Pear Deck. So now we're going to look at what are called motion or particle diagrams. And these are a series of, usually they're dots, and they record an object's position usually after each second. So each dot represents a second in time. And I'm going to go to some particle diagrams. And I want you guys, first of all, to circle for me the letter. I just want you to circle the letter of the particle diagram here that's moving with a constant positive velocity. And there's 2 or 3 of them that are moving with constant positive velocities. But I want you to circle the one that's moving with the slowest constant positive velocity. So take a minute and circle the letter of the particle diagram that's moving with a constant positive velocity, and it's the slowest of all the ones on this diagram, the slowest constant positive velocity. Take a minute and do that. Again, you're just circling the letter of the one you think has the slowest positive constant velocity. All right, I'm going to pull up some responses real quick and just see what you guys thought. So here's a C. I see B. There's a D, another D. I saw a B. All right, I'm seeing several Bs, I'm seeing several Ds. There's an F. So we're kind of all over the place. But it looks like mostly you guys are stuck between B or D. So I'm going to tell you the answer here is B. And I'm going to go back to my PowerPoint for just a minute. So go back to the PowerPoint screen with me. And make sure you mute your microphone. I can hear a lot of background noise going on there. So remember that the time between each one of these dots represents 1 second. So if we look at B, between 0 and 1, this thing goes 1 meter. In the next second, it goes another meter. In the next second, it goes another meter, and then another meter, and another meter, and another meter, and another meter. So this thing is going forward, and it's essentially moving forward with a velocity of 1 meter per second. Now, on the other hand, D, it's also going forward, but every second it's going this far, 3 meters, 3 meters, 3 meters. So that means that this thing has a velocity of 3 meters per second. It's going faster. Somebody unmute and tell me another one of these objects that's moving forward with a constant positive velocity.
A.
A. And what is that velocity? Somebody tell me what that velocity is on A.
2 meters per second.
Yep, 2 meters per second, because every second it's going 2 meters. So this has a constant positive velocity of 2 meters per second. All right, so now let's look at C. Who can tell me what's going on in C?
It's moving faster.
It's accelerating.
That's the word I was looking for. It's accelerating. Because notice in the first second, it doesn't go very far. In the second second, it goes a little bit further. The third second, it goes even further. The fourth second, even further. And the fifth second, even further. So this thing has a positive velocity. And what kind of acceleration? What's the sign of the acceleration here, guys?
Positive.
Positive. And we know that because what's happening to the thing?
It's increasing.
Yeah, its speed is increasing. So now let's look down at D. So what's happening in D?
It's a constant velocity, so
I'm sorry, I meant E. What's going on in E?
it's slowing down.
Yeah, so this thing's at the first second, it goes really far, right? It's going fast. Second, it doesn't go nearly as far. Third second, it goes even a shorter distance. Fourth second, not going far at all. Fifth second, almost stopped, and it looks like it probably is stopped from there on out. So we could say this thing has a positive velocity, but what's going on with its acceleration?
Deaccelerating.
Yep, it's negative. And again, we know that when those two are opposite signs, slowing down. All right, and then the final one is kind of the same thing, right? F, It's going really fast to begin with. It goes a long distance. Then in the second, a shorter distance. The third second, even a shorter distance. This one too has a positive velocity and a negative acceleration. And we know that because it's slowing down. Each second, it's going less distance. All right, any questions on the particle diagrams? All right, let's go back to Pear Deck screen now. So I'm hoping these equations look familiar to you. These are the kinematic equations, and you should have used these a lot in your class already. So this first one is the final velocity equals the initial velocity plus the acceleration times time. The second one, final position equals initial position plus initial velocity times time plus 1/2 times acceleration times time squared. And then that final one is final velocity squared equals initial velocity squared plus 2 times the acceleration times essentially the displacement, the final position minus the initial position. You got to remember that these equations only work when there's uniform acceleration, when the acceleration is the same throughout the whole problem. Constant acceleration might be another way to say that. So these equations only work under constant acceleration. Another equation you should be familiar with is the one at the very bottom of the screen right now, and that is that displacement equals velocity times time. That's if an object is moving with a constant velocity or zero acceleration. All right, so now let's look at the next slide. So acceleration due to gravity is really an example of uniform or constant acceleration. We know that the acceleration due to gravity is abbreviated with a little g. The real value of it is somewhere around 9.81 meters per second square. But in physics 1, we always use the value of -10 meters per second square. And the negative tells us it's down. Things always accelerate due to gravity down toward the ground. In English units, just for you to know, it's about -32 feet per second square. You'll never use that value in this class. That was just for comparison. But just remember that the acceleration due to gravity is sort of a special case of uniform acceleration. All right, so now we're on a multiple choice question. So I want you guys to take a couple of minutes, read the question, and go ahead and type in what you think the correct answer is to multiple choice question 1. Again, go ahead and put in your answer to multiple choice question 1. I'll give you about a minute or minute and a half to do that. All right, so take about 10 more seconds to get your answer in. All right, I'm going to pull up your responses just to see what you guys thought. So it's looking like a lot of C's and a lot of D's. Not too many A's and B's. Let's see what we got here. So key thing to remember is this is a velocity time graph. And we're looking for what is true of the distance. Again, from a velocity time graph, how do we find distance or displacement, guys? Somebody unmute and tell me.
The area under the curve.
Area under the curve. So if we want to find the area under the car curve, that's a triangle, right? The area under the truck curve is a rectangle. Which one of those is going to have a much bigger area? Truck or car?
The truck.
The truck. It's essentially twice as much, right? So the answer here is D. The truck traveled further than the car. Now, some people look at it and they see that their lines crossed. So some people think that's the same. What's the same at that point where the two lines cross?
Velocity.
The velocity. So the car, what can we say about the truck? What's the truck doing during this whole time interval?
He has a
Constant
constant.
velocity.
A constant positive velocity, right? The car, what's the car doing during the whole time interval?
Accelerating.
It's accelerating. It starts out about 0, and then it speeds up the whole time until it eventually gets as fast as the truck. Even though it's as fast as the truck at that point, it wasn't the whole rest of the time interval, which means it hasn't gone as far. And that's why our answer here is D. The area under the truck curve is much bigger than the area under the car curve. That means the truck traveled further than the car did. All right, let's go to question 2. Same thing, take about a minute or so and try to answer question 2. Notice that bolded word in the question, speed. So pay attention to that word. That's the key word in the question. So go ahead and enter your answer. Paying attention to the keyword speed. All right, got about 10 more seconds to put in your answer. I'm going to look at your responses. So we're saying a lot of A's and a lot of D's. Oh, we got a surge of A's there. So a lot of people have jumped on the A bandwagon. Let's see. So a lot of you are looking at this slope of this line, and you're thinking, well, hey, slope of a velocity time graph is what? What's the slope of a velocity time graph?
Acceleration.
Acceleration. And it's a positive acceleration. So A makes sense there. But I cautioned you to pay attention to this word, speed. Acceleration's a change in what?
Velocity.
Velocity. And what matters in velocity that doesn't matter in speed?
Direction.
Direction. That's going to come back to bite those of you who said A right here. Because notice, this thing starts off with a speed of about like -2.5, right? Well, let's put it this way. The velocity is -2.5, which means the speed is just what? 2.5. And as we move forward, what's happening to the speed as we go from here to say here?
Decreasing.
It's decreasing, right? So it slows down to 0 right here at the x-axis. And then once we get to the x-axis, the speed starts to go back up again. It becomes positive, right? So the speed goes from a negative value to 0, and then it goes from a 0 value to a positive. If this question had said velocity here, A would have been the right answer. But because it said speed, the thing's going pretty fast at first, -2, -2.5. Eventually it goes a speed of 0. And then it speeds back up to a speed of about +4. So our answer here is it decreases, then it increases, and that is answer D. And that's one of the tricky kinds of questions they're going to throw at you on the AP exam. So make sure you look at, are they talking about speed or are they talking about velocity? And pay really close attention to the differences between those two. Same goes for distance and displacement. Look at what they're asking for. Pay attention. Whoops. All right, so let's look at question 3 now. And again, I want you to take a minute or so and mark your answer to question 3. Which of the following represents an object having 0 acceleration? Make sure you're looking at the axis and the labels on those axes of each graph. Go ahead and input your answers now as soon as you figure them out. You can keep putting in answers. I'm going to look at your responses. So it looks like the popular choices here are B and C. So I'm going to go back to my PowerPoint screen for a minute. So you guys follow me back to the Zoom screen. All right, so let's just look at these graphs one at a time. Notice that this is a position versus time graph. And that position versus time graph has a nice constant slope. On a position time graph, what does a constant slope tell you?
There's a constant velocity.
It's a constant velocity. And if we have a constant velocity, that means 0 acceleration, right? So A looks like a good answer. Now let's look at B. B is a velocity time graph. How do we find acceleration from a velocity time graph?
The slope.
The slope. And what's the slope of a nice horizontal line?
0.
0. So once again, this is A equals 0. So A and B are both right. Now let's go down to C. C, this is a velocity time graph. And again, slope on a velocity time graph represents acceleration. Here we have a negative slope, which means we have a negative acceleration. It's not 0. D, another velocity time graph. Here we have a slope that's up and to the right, so that's a positive slope, which means a positive acceleration, not a non-zero acceleration, which means our answers to this one are A and B, which would be choice C. Anybody have questions on that one for me? All right, let's go back to the pair deck then. And let's look at question 4. All right, you guys go ahead and answer the question for me here. Read the prompt and answer that question. And notice here it's only asking for the change in velocity. I'm going to go ahead and take a look at the responses that are popular. So B and C seem to be our big ones. All right, I'm going to go back to my PowerPoint screen for a second, so go back to Zoom with me for just a minute. So remember, to find a change in anything, in this case, we're looking for a change in velocity. It's the final minus the initial. So what's our final velocity in this problem? Somebody help me out. Final velocity.
Negative 35 meters per second.
Negative 35. It's got to be negative 35 because it says 35 to the left. So negative 35 meters per second minus the initial velocity, which was positive 40. Which means our change in velocity is negative 75 meters per second. So C is what we were looking for on that one. Does that make sense? You got to remember that positive is to the right, negative is to the left. Or if you're dealing with vertical stuff, positive is up, negative is down. Don't forget to do that. All right, let's go back to the Pear Deck screen. And let's look at question 5. There are 10 of these questions, guys, so we may go 5 or 6 minutes past 5 o'clock. But I want to go ahead and work through them all. So those of you who can stay around until about 5:05 or so, we should be finished by then. All right, go ahead and do the same thing on question 5. Same prompt, different question about that prompt. Go ahead and try to answer question 5 for me. You might need a calculator on this part. So we're looking for the acceleration. All right, I want to take a quick look at the popular answers so far. So it looks like B is by far the most popular. And again, I'm going to go back to my PowerPoint for a second. Remember that acceleration is change in velocity over change in time. We already calculated the change in velocity in the last problem was negative 75 meters per second. And the time over which that happens is 0.005 seconds. So we just divide that out. I'm having battery issues here, guys. Let me make sure I'm plugged in and ready to go. There we go. So let's go negative 75 divided by 0.005. And we end up with about 15,000. In this case, negative 15,000 meters per second squared. So choice B is what we were looking for on that one. Any questions on that one? All right, let's get back to the Pear Deck then. All right, here's question 6. Just for the sake of time, I'm going to work through this one with you. I do want you to go ahead and mark an answer once I finish in Pear Deck so that you get credit for having done it. But I'm going to go back to the PowerPoint. This one takes a minute, so I want to go ahead and work it from the PowerPoint. So we have Quicksilver, who runs at a speed of 220 meters per second. He accelerates at a rate of 20 meters. That should say he then accelerates at a rate of 20 meters per second square for 6 seconds. What is Quicksilver's displacement during the last 2 seconds of the 6-second time interval? So I'm going to work from this equation. Delta x equals VOT plus 1/2 AT squared. That's one of my kinematic equations. And first of all, I'm going to work at 6 seconds. So I'm going to say for the whole 6 seconds, delta x is the initial velocity, 220. And I'm going to leave off the units. You should never do this, but just so that I have room to do the problem, I'm going to leave off the units. 220. He does that for 6 seconds plus 1/2 times his acceleration of 20 times the time squared, 6 seconds squared. All right, so if I do the math on that, multiply all that out and add it up, I get a displacement of 1,680 meters. That's how far Quicksilver runs during the whole 6 seconds. If I wanted to know how far he went just during the last 2, what would be the other thing that I ought to calculate here? What's the trick on this problem? Somebody help me out.
Finding the displacement within the first 4 seconds.
Exactly. Calculate how far he went during the first 4 seconds. So let's use the same equation, VOT plus 1/2 AT squared. So 220 times the time of 4 seconds plus 1/2 times the acceleration of 20 times 4 seconds squared. Calculate that out. Multiply, add, end up with a delta x of 1,040 meters. So this is how far he went during the first 4 seconds. This is how far he went during all 6 seconds. So how do we figure out how far he went during the last 2 seconds?
You subtract the 2.
Just subtract 1680 minus 1040, and we end up with 640 meters. So go back to Pear Deck for me. And go ahead and mark for me C, just so that we got credit for all of you putting in an answer there on that one. Because again, you're going to get a copy of this, and this way you'll know what the right answers are when you get your copy. So make sure you mark C. All right, I'm going to go ahead and go to question 7. So Joe throws a 3-kilogram ball horizontally from the edge of an 80-meter cliff with an initial velocity of 30 meters per second to the right. What is the ball's vertical velocity at the instant before it touches the ground? And again, for the sake of time, since we're already over time, I'm going to go back to PowerPoint, the Zoom screen, and I'm going to work through this with you so we can do it pretty quickly here. So let's just kind of draw out what's going up here. Let's say here's the cliff, and he throws this ball horizontally. So it starts off with only a horizontal speed. When you're working projectile problems like this, you need to think about what's going on horizontally and what's going on vertically separately. So at the beginning of this problem, how fast is this ball moving vertically? Somebody help me out. If he throws the ball horizontally, what's its initial vertical velocity?
0.
0. All right. What's its acceleration vertically?
-10 meters per second.
Yep, because it's acceleration due to gravity, right? It's accelerating due to gravity at -10. And what's its, by the time it gets to the ground, what's its vertical displacement?
meters.
Okay, it's not 30. Look again.
Negative 80 meters.
All right, key answer there. Somebody knows what they're doing. He said that the displacement is negative 80 meters because the cliff's 80 meters tall. And this thing is falling. It's going down 80 meters. That negative is crucial. So we know an initial vertical velocity, we know an acceleration vertically, and we know a displacement vertically. And we want to know what is the ball's vertical velocity at the instant before it touches the ground. All right, so what would be the best way to start in terms of going about this problem? What should we find first? I think the easiest way to start is to find how long it takes this thing to get to the ground. And I'm going to go to a kinematic equation. And I'm going to write delta y here instead of delta x because we're working vertically. But it's the same equation, VOT plus 1/2 AT squared. Remembering that our initial vertical velocity is 0, which means this whole term goes away because VO is 0. So essentially we're working with delta y equals 1/2 AT squared. I'm trying to solve for time. So I'm going to go ahead and rearrange this equation for time. So I'm going to multiply both sides by 2 to get rid of that 1/2. I'm going to divide both sides by a. And I'm going to take the square root of both sides. So this is just this equation, this whole equation, solved for time. And then I'm going to plug in my values. So it's 2 times delta y. Delta y is negative 80 over my acceleration, which is negative 10, and then take the square root of that whole thing. And when I do, I end up with a time of 4 seconds. So it takes this thing 4 seconds to get to the ground. That's not the answer I'm looking for. I'm looking for the vertical velocity, but I've got to know that time to get to that velocity. Once I have the time, I can use another one of my kinematic equations to find the velocity, and I'll just use this one. Final velocity equals initial velocity plus acceleration times time. So my final vertical velocity is going to be equal to my initial vertical velocity, which was 0, plus my vertical acceleration, negative 10, times the time of 4 seconds. Multiply that out, I'm at negative 40 meters per second. So let's go back to the pear deck screen, and you guys go ahead and mark for me negative 40, which is D, and that way you've got that right answer, negative 40. Everybody okay with that one? We're almost finished. Bear with me for just a couple more minutes and we'll finish up. Like I said, there's 10 questions. We're on number 8, about to start number 8. All right, so number 8 is a continuation of 7. Same prompt. This time though, what are the vertical and horizontal components of the ball's velocity at t equals 2 seconds? All right, important question. You guys tell me what happens to the horizontal velocity during projectile motion, assuming that we don't pay any attention to drag or air resistance.
Nothing.
What happens to the horizontal velocity of an object during projectile motion?
It doesn't change.
It doesn't change. It remains constant. So this thing started off initially with a horizontal velocity of 30, which means the whole problem, it has a horizontal velocity of 30. Let's go back to the PowerPoint screen for a minute, the Zoom screen. And let's try this. So we know that the horizontal velocity is 30. So our answer's got to be either A or D. The vertical velocity, remember the vertical velocity we can find using this. We know that it starts off with 0 vertical velocity. It accelerates at negative 10. And in this case, it does that for 2 seconds, which means our final vertical velocity is going to be negative 20 meters per second. So we have a horizontal velocity of 30 meters per second. And by the time we get to 2 seconds, we've got a vertical velocity of -20. So let's go back to Zoom, Pear Deck rather. And go ahead and mark for me on that one, choice A. Make sure you get the right answer marked. Horizontal velocity of 30 meters per second, vertical velocity of -20 meters per second. All right, 2 more problems to go, both of which will be pretty quick. And again, I'm going to go back to the PowerPoint to work this one out. So same problem. This time we want to know what's the resultant velocity of the ball at 2 seconds. What's the resultant mean, guys? Somebody tell me what the word resultant means.
Final velocity?
Yeah, the sum. So we need to add the horizontal and the vertical components together to get a total velocity at 2 seconds. And we have to do some vector addition to do that. When you're doing vector addition, the easiest way to do it is to use what's called the tip to tail method of vector addition. And I like to always start with my horizontal component. It makes my pictures easier. So our horizontal component was 30 meters per second to the right. Let's pretend that's a horizontal line. Not quite horizontal. And then my vertical velocity was -20. So when we're adding those 2 vectors, we go to the tip of the first vector and we start with the tail of the second one and we draw it in like so. We find our resultant by connecting together the tip of the tail of the first vector to the tip of the second vector. This line is my resultant. It represents the sum of those 2. In this case, we know this is a 90-degree angle right here. What's the easiest way to find R?
Pythagorean theorem.
Yeah, so do the Pythagorean theorem and just do R squared equals 30 squared plus 20 squared. Solve that out for R. And when you do, you come up with 36.1. Now, a lot of people would stop right there and they would say, okay, my answer is 36.1 meters per second. But remember, in velocity, velocity is a vector. Direction matters. And when we have a vector that's not straight up, straight down, straight to the right, or straight to the left, we have to give that velocity in terms of an angle. And the angle that we typically like to find is the angle between the horizontal and the resultant. The smallest angle between the horizontal and the resultant, which would be that one. We can find that angle real easily using what trig function?
Tangent,
Say again?
tangent, or
Tangent.
inverse tangent.
So I'm going to call this theta, and I'm going to say that the tangent of my angle theta is equal to the opposite side from that angle, 20, over the adjacent side to that angle. So I'll go 20 divided by 30 and take the inverse tangent. And when I do that, I get an angle of 33.7 degrees. And in addition to the angle measurement, you need to give some directional words to describe how that's going. So I'm saying that this thing is going to be going 36.1 meters per second at an angle of 33.7 degrees below the horizontal and to the right. There's other ways you could write that, but that's probably the most straightforward way. 36.1 meters per second, 33.7 degrees below the horizontal and to the right. So let's go back to Pear Deck and go ahead and mark for me choice B so that you have that right answer marked in your Pear Deck takeaway. And then we've got one more problem and we'll call it a day. All right, this one doesn't require any work, so we're going to do it from right here. I want you guys to go ahead and look at this problem and mark what you think the right answer is on question number 10. And notice the key word here, speed, is highlighted again. So pay attention to that word speed. All right, here's some things to think about. What do we know is going on with the horizontal component of the speed at each of these locations, A, B, C, and D? If this question was just about the horizontal component of the speed, what would our answer be? During a projectile motion problem, what happens to the horizontal component of the velocity?
It stays the same.
Stays the same. So if this was asking about the horizontal speed, our answer would be A equals B equals C equals D. But that's not what it's asking about. It's asking about the total velocity, the resultant velocity. So let's look at A. At A, this person just kicked it. What can we say about the vertical velocity at A? If it just left his foot, what's going on with the vertical velocity?
It's
Fast or
zero.
slow?
Slow.
Well, it just came off his foot. It's going as fast as it will ever go vertically once it leaves his foot, right? Because his foot is what applied the force that made it go. Once it leaves his foot, can't speed up anymore. But what can happen to its vertical velocity after it leaves his foot? What force is acting on it after it leaves the foot?
Gravity.
Gravity. And what's gravity doing to the vertical velocity?
Slowing it.
Slowing it down. So between A and B, this thing slows down. Between B and C, it slows down. All right. And essentially at C, what's its vertical velocity at C? What's an object's vertical velocity at its highest point?
0.
0. So it still has a horizontal velocity, but vertically it has 0 here. And then it starts going back down. What starts happening to the vertical speed on the way down?
Increases.
It increases. And notice that B and D are at the same height. So what does that mean about their vertical speed since they're at the same height?
It'll be the same.
They're the same. So that being the case, which answer is the right answer?
B.
B. A has the greatest velocity. B and D have the same. C has the lowest velocity. So B is the right answer there. All right. Make sure you mark that one, guys. I took you about 20 minutes over today. I apologize for that, but I wanted to get through this presentation. We are going to do these things each week, and we'll go through a different unit each week. Next week will be Unit 2, Dynamics. We'll deal with forces. Thank you guys for being here. You should get a Pear Deck takeaway 20 or 30 minutes after I close this session. So be looking for that. To find it, you'll find it under Google Drive, shared with me. You should have either a file or a folder that says takeaways. You should be able to find it there. But again, I want to thank you guys for being here. Are there any questions I can answer for anybody before we call it a day?